Hello, my name is Ionic Rob, and in this video I will be showing you how to calculate the atomic packing factors of the three common metallic structures. The three are body-centered cubic, face-centered cubic, and hexagonal close-packed, shortened to BCC, FCC, and HCP respectively. Simple cubic, however, is not a common metallic structure, and the only element known to crystallize in this form is polonium. Examples of elemental materials that crystallize into the three common metallic structures are shown on the board. Pictures of the non-reduced models of the crystal structures will be on the whiteboard for the remainder of this video. For the HCP structure, I have shown three different pictures, with respect from left to right and top to bottom. The first picture shows the structure in 3 dimensions, the second picture shows the projection of the unit cell down the z-axis, and the third has the unit cell repeated 4 times to show the hexagonal nature of the unit cell more clearly. For those who are unaware of what the atomic packing factor is, it is the fraction of the volume of a unit cell occupied by the atoms of the crystal structure. In our case, we are only looking at the crystal structures formed from a single element, so each of the atoms in the unit cell can be approximated to being spheres of the same radii. To determine the atomic packing factor values, we first have to find the relationship between the atomic radii of the atoms of that structure with the lattice parameters of that structure. The three base vectors A, B, and C of a unit cell lie along the three axes x1, x2, and x3 respectively, as shown on the board, and define the form of the parallelepiped of the unit cell. The magnitudes of the base vectors and the angles between them are the lattice parameters of a unit cell. In the cubic crystal system, these three axes are mutually perpendicular to one another and are commonly called x, y, and z respectively. In this system, three base vectors all have the same magnitude of value A. In the hexagonal crystal system, as observed in HCP, the angles alpha and beta are equal to 90 degrees. The angle between the base vectors A and B is called gamma and is equal to 120 degrees rather than 90 degrees. In the case of HCP, the magnitudes of the base vectors are not all the same. The ideal magnitude ratio of C to A is equal to root of 8/3. The three red lines drawn below are the distances used in determining the relationship between the lattice parameters and atomic radii of each of the structures, i.e. the R to A ratios. In BCC, the distance of the red line L is equal to 4 radii, as the atoms involved make contact with one another, and L is also equal to root 3 of A. In FCC, the distance L is equal to 4 radii, as the three atoms along that distance make contact with one another, and this distance is also equal to root 2 of A. In HCP, the distance L is the distance between two neighbouring atoms of the same x3 position, hence the value of L is also equal to A. Equating the two forms of L for each of the structures gives the relationship between R and the lattice parameter A. These values are root 3/4A, root 2/4A, and a half A respectively for BCC, FCC, and HCP. The equation for the atomic packing factor is written below with the Greek letter eta representing it, where N is the number of atoms contained per unit cell, V atom is the volume of an atom of that crystal structure, and Vu is the volume of the unit cell itself. This equation can be thought of as the fraction of the total unit cell volume that is occupied by the volume of the atoms of that unit cell. Let's first work out the number of atoms per unit cell for the three structures. Depending on the crystal structure and the placement of atoms within the unit cell, an atom can contribute a certain fraction of their volume to the volume enclosed within the unit cell's parallelepiped. This concept can be shown by the non-reduced diagrams of the structures in the top left hand of the whiteboard. On the whiteboard, the values of how much each atom contributes to the volume of the unit cell is dependent on the position, is in relation with a cubic unit cell and not for an hexagonal unit cell. In BCC, there are 8 corner atoms and 1 internal atom in the unit cell, which, taking into account the fraction of their volume enclosed within the unit cell, makes the total number of atoms per unit cell equal to 2. For FCC, there are 8 cube corner atoms and 6 cube face atoms, making the N value of FCC 4. To calculate the number of atoms in HCP is slightly different to the previous two, as not each corner atom of the parallelepiped contributes the same amount of atomic volume. Looking back on the z-axis projection of the HCP structure, we have 4 atoms at the corners which lie at the 120 degrees points and 4 atoms at the 60 degrees points. Take note that there should be an internal atom on the diagram. The atoms at the 120 degrees points contribute 1/6 of their volume, and the atoms at the 60 degrees points contribute 1/12 of their volume to the unit cell. Thus adding the contribution gives us a total of 2 atoms per unit cell in the HCP structure. Now we need to determine the volumes of the 2 different types of unit cells that we will encounter, VU being as defined earlier, VUC being the cubic unit cell volume, and VUH being the volume of the unit cell of the hexagonal close-packed structure. Using the scalar triple product as shown on the whiteboard, we can obtain the volume of the parallelepiped describing the unit cell. To use the scalar triple product to calculate the value of the cubic unit cell is a little trivial, as it's simply a cubed, but I'll show the working still to obtain it. The angle for the dot product is 0, as the vector product of base vectors b and c is parallel to base vector a, and in the vector product of b and c, the anti-clockwise angle between them is 90 degrees. This means the scalar triple product becomes the product of the magnitudes of a, b and c, but as the 3 base vectors have the same magnitude of value a, this means VUC equals a cubed, as previously stated, i.e. the volume of a cube of length a. The value of the HCP unit cell will now be calculated with the aid of its base vectors drawn on the whiteboard. The difference between the base vectors of this structure to the previous, so the magnitude of c is not equal to a or b, and that the anti-clockwise angle between a and b is 120 degrees. Using the scalar triple product, the vector produced from the cross product of a and b is parallel to the base vector c. This means VUH now equals CAB sine 120 degrees. Now using the ideal ratio of c to a, we can have the volume of the unit cell in terms of a. The value of VUH is equal to √2 of a cubed. The final step to working out our atomic packing factors is to calculate the volume of the atoms. The volume of a sphere is 4/3 pi r cubed, where r is the atomic radius, so for our structures we have to input the atomic radius for each one in terms of a to obtain the atomic volume for each of the structures. When we input the atomic radius for BCC, we obtain this when we directly put it in. Then, by simplifying, we obtain the volume of that atom in terms of the lattice parameters of that crystal structure. Expressing the atomic volume in terms of A will make further simplifying easier. We can also work out the atomic volume for the atoms of the FCC crystal structure in terms of A. Inputting the atomic radius for FCC, we obtain this value, and for HCP we obtain this value for the atomic volume. Now we can begin to work out our atomic packing factors. Inputting our previously calculated values, we obtain this. As seen, the a cubed term does cancel out, with the atomic packing factor being pi √3 all over 8. This atomic packing factor value means that 68.0% of the total volume of the unit cell is occupied by the volume of the constituent atoms. Repeating this for the FCC, we obtain this equation, which can be simplified to pi √2 all over 6. I've left the atomic packing factor value of HCP for you to calculate, using the equation given to you earlier. Strangely, the atomic packing factors of FCC and HCP are identical, due to their structures originating from the stacking of hexagonal close-packed layers. I hope this video has cleared up some issues with obtaining the atomic packing factors of the 3 common metallic structures. The same principles here can be applied to other more complicated crystal structures, such as diamond.